welcome to the TMSI Expert Talks. My name is Leonie Terstegen and I will be your host for today. First of all, I want to give you my best wishes for the new year. I hope you all enjoyed the holiday as much as I did. And I'm really excited to start off this new year with this webinar because we're not only having one speaker, but we actually have four. And of course, I want to give them an extra warm welcome. I will start with Dr. Cruijsen, who is Associate Professor at the Erasmus Medical Center in Rotterdam. And there he's leading a research group in the Department of Rehabilitation Medicine. Then we have Maria Carla Piastra, who is a postdoctoral fellow from the University of Nijmegen. Then we also have Joris van der Cruijsen, who is a PhD candidate in his fourth year at the Erasmus Medical Center in Rotterdam. And last but not least, we have Manoochehri, who is a postdoctoral fellow from the University of Delft. She couldn't be here with us today, but she was so kind to record her presentation so we could still enjoy her research. The topic of today's talk is individualizing transcranial direct current stimulation to improve motor learning in stroke. And before I give the word to Dr. Selles, I would like to mention some house rules. First, as an attendee, your microphones are automatically muted. So if you have a question, you can use the Q&A button on the bottom of your screen. And after all the presentations, I will go through the questions one by one. Or you can save your question for after the presentations, and then you can use the raise your hand button and I can unmute your microphone so you can ask the question to one of our presenters. Well, then I hope you all enjoy the webinar and I would like to give the word to Dr. Selles. The floor is yours.
Okay, thank you very much, Leonie, for introducing us and especially, of course, also for inviting us to be able to give this TMSI expert talk. It's a great honor and a really nice start of the new year also. So for all of you also still a very happy new year. The year started very lively yesterday night, but of course today we'll talk about science. Leonie already introduced us a little bit. So there are four speakers, but we're really talking about one project that we would like to present to you today, which is about, with the final goal actually to improve motor learning in patients post-stroke and the application of transcranial direct current stimulation. And this is actually a part of a large research project sponsored by NWO. And it's a series of combined projects. This is one of the sub-projects where we work together with a number of different partners that you see over here. So I'm with the Erasmus MC, but we have partners, and yours is also from Erasmus MC. We have partners from the TU Delft, especially for the EEG analysis, from Radboud University, especially about the head conductivity analysis. We have a clinical partner, Rijndam Rehabilitation Center, and TMSI is also a partner, also because we use part of their equipment, but they've also helped us to innovate the way that we can combine transcranial direct current stimulation with EEG recordings. So what I would like to do, or what we would like to do today, is to give you an overview of this project, where in the next minutes I will give a general introduction of why we do this study and how what is basically the challenge that we are trying to solve. And then the different researchers that were already introduced will further on present their part of the work and how this all connects together. So the goal of my short presentation is to introduce to you the topic. I don't really know what the background of every one of you is. So maybe you all know transcranial direct current stimulation, but it's a technique that has been around for quite a number of years. It's basically a relatively simple technique where you use a direct current stimulation. You apply electrodes to the brain and you basically modulate the brain, which is of course something that that has been done in many different ways in the past already. And in recent years, it's become really popular, where you can even buy a device like this that is supposed to make your gaming a lot better. So it's even kind of a doping for the brain, if it would work. And I will discuss with you later on that it's certainly not completely clear that this is effective, and it's actually to some extent also quite controversial. Well, there is in fact a lot of literature, and for the scope of this research, I don't want to go too much into the details of how this works, but there's a lot of research that's been going on from the level of cell physiology, looking at how direct currents influence neurons, to animal research, human research in terms of non-patient populations, and there's a lot of patient studies. Also for other applications, today we will be talking about motor learning and stroke, but it's also, i-tDCS is also something that's, for example, very often used to as a treatment in depression. And the idea generally is that with a direct current, you can change the polarization of neurons in the brain. From research, we know that this, among others, influence BDNF. And for the motor system, a very measurable effect is that it influences the excitability of the brain regions. And this is classically measured with a technique called transcranial magnetic stimulation, TMS, where you stimulate the motor area of the brain, and with that stimulation you evoke an EMG response in one of the hand muscles, which you can measure. And it's been very often reported that with transcranial or with i-tDCS, so with this brain stimulation, you can either up or down regulate this excitability, which means that if you gave the same TMS pulse after i-tDCS, you can either get a larger or a smaller response. And that would be a measure of the excitability, how easy the brain can be excited. And that could be one of the mechanisms in which you basically up or down regulate the brain. If you go to the clinical effects, then in the last probably 15 to 20 years, there's been a lot of studies showing or investigating that you can use i-tDCS to basically enhance motor learning. The idea is that only i-tDCS would not have an effect, but if you would combine it to, for example, some motor learning task, that subjects would be able to learn this task better. And since we assume that a stroke patient with a brain damage needs to relearn its movement, it's a very attractive idea that you could use i-tDCS in addition to rehabilitation treatments and increase the amount of motor learning that stroke patients have. And as an example of such a study, and there are actually many, is this study in Frontiers in Human Neuroscience, where they had stroke patients perform a motor test, which was basically moving a mouse in a pattern over a screen. So it's basically an arm movement. And they had two groups. They had a i-tDCS group and a sham group. One of the nice things about i-tDCS is that you can have sham i-tDCS, which feels very similar to patients as real i-tDCS. And what this study shows is over here in the darker error bars, that the group that had i-tDCS tended to learn much faster to perform this movement actually than a control group. So that's a really nice study, but and it's actually one of the studies that we try to replicate in our study with the idea of further on trying to even optimize this. But I think therefore it's also important to mention that that some of the more positive findings in the past seem to be difficult to replicate, not only in our group, but also in a number of a number of different groups, other groups internationally. And this is a publication that we presented in Brain Stimulation in 2017, where we basically replicate the findings on the left with actually 4 different groups, very well sampled stroke patients. And in fact, quite unfortunately, we failed to demonstrate a general tDCS effect. And actually, in terms of the controversy about tDCS, we also tried very recently to replicate these basic findings on the motor excitability. And just in December last year, we published this presentation, this study also on brain stimulation, where we did a very large pre-registered study, and we in fact failed to find a systematic tDCS effect. So I think it's important to mention up front that tDCS is in that sense quite controversial. And what we will try to argue in this presentation is that if you start thinking about how you would apply this in stroke patients, you may need to take into account a lot more detailed variables to think about ways that how it could be effective. So if you would summarize the effects of motor learning on stroke, there are some promising results, but these results of clinical studies tend to be inconsistent, positive and non-positive findings. And the reasons for this may include that we still have a lack of mechanistic understanding of how tDCS works. So how would this enhance motor learning? And if we would understand that better, we might be able to apply it better. We may also lack tools to target the tDCS treatment very specifically to individual patients. And that's the topic of this presentation today. And basically the topic of this research project. And what do we mean with this? One of the important things is that if you apply tDCS to stroke patients, then most tDCS studies assume that you either want to stimulate the affected or the non-affected stroke hemisphere, and especially the motor area. But what we know from stroke patients is that if there's a large brain damage that has occurred, then the motor areas of stroke patients tend to reorganize. So if you would want to target a specific area, then this, for example, the area that controls the affected arm, then this area might be located differently in different stroke patients. And it would be quite difficult to assume that in all stroke patients, we may need to target exactly the same area. So that's where we think that there's a need for individualization. And one of the things to do this would be with EEG, where we can identify that stroke-specific area. So that's one of the things that we will present. So that would be targeting a specific functional area. But the other thing that you could wonder about is if we really want patients to learn something, we're talking about motor learning, and can we identify the networks involved in motor learning, and can we maybe also measure if tDCS either up or down regulates this motor area? So there's also a question on where is motor learning organized in the brain? Can we directly measure that, and is that influenced by tDCS? The other thing is that if you would know which area to identify, there's also a question on what electrode configuration do you need to optimally reach that area? And what's very specific for a stroke brain is that there could be a smaller or a larger lesion, which may very often be filled with brain fluid, for example, which may alter the optimal electrode configuration that is needed to target a specific brain area. So that would mean that we need models of the brain, that connectivity models of the brain, and create algorithms to basically calculate the optimal electrode configuration. So that's another part that we will present on today. So what is the flow of the presentations? After my introduction, Maria Carla Piastra is a postdoc from Radboud University, and she will talk about simulating brain stimulation and estimating lesion conductivity with tDCS and EEG in stroke. Then Joris van der Cruijsen will present on tDCS combined with EEG to further individualize the tDCS stimulation. And Manoochehri will talk about conductivity analysis in EEG, which we think is very important for motor learning. So that's the basic outline. We plan to do the presentations directly after each other, and then feel free to already pop in some questions in the Q&A, but we will answer them at the end of the session. So without further ado, I will give the word to Maria Carla.
Yes. Here I am. I think everyone can see my slides. Now, not share. Present. Okay, so good afternoon to everyone, and Happy New Year also from my side. Today, as Ruud just explained, I will be talking about simulating brain stimulation and estimating lesion conductivity with tDCS and EEG. So as Ruud just explained, what is the interplay between tDCS and motor learning in chronic stroke patients? Well, the effects or the effectiveness was proven to be not consistent in literature. And one of the causes might be given by the fact that non-optimal electrode configuration is applied. And in general, there are techniques aiming at individually optimizing the target of the stimulation. And in order to talk about that, I have to introduce volume conduction simulations, or what is part of the title, what does it mean to simulate brain stimulation? So when talking about volume conduction modeling, I can give a couple of examples. In EEG, if the final goal is to compute or to perform source reconstruction, first we need to compute the potential at the electrodes, knowing the source inside of the head. And in the reciprocal way, in tDCS, if the final goal, as Ruud explained, is to achieve and to obtain the optimal configuration for the electrodes, first we need to compute the potential inside of the head, knowing the source at the electrodes, knowing the current that has been injected. If we give some details about volume conduction modeling, which are the ingredients of a volume conductor? First of all, we have to construct the so-called head model, where electrical and geometrical features are merged together. This can be a very coarse representation of the head, like a sphere with several compartments, or we can achieve a more accurate and realistic shape of the head. For example, starting from MR images. Another ingredient is the sensor, or the model of the sensor, which can have different shapes, size, and material. We have to model the source, for example, in the case of tDCS, of the injected current. And we have to pick a method that has to be used to perform our brain simulations. And in general, there's a vast spectrum of different numerical methods. And just to give further keywords, two examples of these methods are given by the boundary element method and the finite element method. So going on and focusing on one ingredient that I mentioned before about the volume conduction model is the electrical features, or in general, the conductivity of the head model. So we know that there's a huge variability among tissues' conductivity. For example, if we think about the cerebrospinal fluid that Ruud mentioned before, that's an extreme conductive tissue or liquid that we have in our heads. And this can be compared, therefore, as the copper part of this electric wire. While the skull works as an isolator in our head, so the rubber part of the electric wire. And this diversity and this difference between conductivities has to be taken into account. Plus, we have variability among humans, and in general, In practice, conductivity values that are used for simulations in the volume conduction model are not consistent in literature and not individualized. In our case, we also have to ask ourselves, what is the stroke lesion conductivity? As Ruud mentioned, the lesion compartment is often modeled as a cavity filled with fluid. But is it always the case? Is it always homogeneous? From this picture, for example, we can see that the stroke lesion is not a homogeneous compartment. So modeling it only with a high value of the conductivity of the CSF, of the fluid, would modify most probably our results. This is what we want to investigate. So we're talking about estimating in general conductivities, in particular the lesion conductivity. There are methods that has been used to estimate individualized head tissue conductivity. This was done in vivo and plus with combined i-tDCS and EEG. An example of this method can be seen in the work of Ostendorp et al., where they focus their attention in estimating human skull conductivity. So our question then popped up, and so we asked ourselves, can we apply such methods with simultaneous i-tDCS and EEG to estimate chronic stroke lesion conductivity in realistic experimental conditions? So to answer that question, let's go through the method that has been used and that we applied in our study concerning the in vivo estimation of lesion conductivity. As a disclaimer, this method is like a proof of principle. We did not use real data apart from DNR images, so we did not record i-tDCS from patients so far, or we didn't use it in the study. So the general idea is to inject current through a pair of i-tDCS electrodes to record the potential generated by the i-tDCS, so that the current that has been injected at the scalp using the EEG electrodes. So a combination of i-tDCS and EEG, we can already see. Then on the other side, build an individual head model based on MRIs and calculate the potential generated in the head model. And now then we will end up having recorded potentials and calculated potential. And by comparing the two, we can determine the lesion conductivity for which the calculated potentials fit the recorded potential. This is the configuration that we use and the head model that has been constructed for one stroke patient. And we added some variability. We examined small and large lesions. And in addition, in order to recreate some experimental challenges that experimentalists will face, we added noise on electrodes. So we changed the position of the electrodes by applying a coronal and a sagittal rotation of the position of the electrodes. And we altered the number of electrodes in the configuration from 8 to 128 electrodes. Going to the results, we could see that the optimization algorithm, when comparing recorded and calculated potentials, converges. So we could find the correct lesion conductivity that was fixed for the recorded potential when there's no noise in the electrode position. We achieved already good results when using only 8 electrodes. So it did not improve significantly or enough the accuracy of the results when going from 8 to 128 electrodes. And but the rotation of the electrode should remain below 0.5 degrees, so around 1 millimeter to achieve good results. And this is a good guideline, for example, for experimentalists. More details hopefully will appear soon in the paper we submitted to Janie. Giving and drawing some conclusions and talking about some future steps, the lesion conductivity as an additional source of inter-individual variability can easily be incorporated in experimental procedures that already combine i-tDCS and EEG. And as such, the accuracy of targeting brain areas for i-tDCS may improve. As a future step, we would proposed to add random noise reflecting the background EEG activity to the skull potential, which we haven't done so far, and to use more accurate head models and the finite element method, using, for example, a combination of already existing software toolboxes like SimNIPS and our own ASH, that is a software tool aiming at semi-automatically create a head model with the lesion compartment already included. Sorry. With this, I would like to thank the first author and the PIs of this study, Joris, Ruud, and Tom, and you for your attention. Thank you. I will stop sharing. And
okay, then I will continue. Can you all hear me?
yes.
Okay, and can you also see my slide?
Yes.
Okay, great. Okay, then I will continue with my part of the individualization of t-DCS, and I will mainly talk about the experimental setting that we are using and how we can use EEG to determine targets for t-DCS. First of all, the equipment that we use. We have a 128 channel EEG cap and an amplifier from TMSI. And we use this in combination with the StarStim 8 from Neuroelectrics to stimulate at maximally 8 channels. And we have adjusted custom platinum stimulation electrodes that we can insert at any of the 128 channels in the EEG cap. A question that might come up directly is why we use platinum stimulation electrodes. That is because the silver chlorides electrodes wear out very fast if you put current through them, and that will result in having a part of the electrode end up on the stimulated scalp. And having platinum stimulation electrodes allows you to stimulate really for a long time without having risk of this. t-DCS in combination with EEG has a lot of potential to be used, for instance, to improve rehabilitation after stroke, because it allows you to stimulate where and when needed based on individual functioning. And as Ruud explained, this is particularly relevant, for instance, for the motor system, where different patients show different activation patterns if they have to do a unilateral motor task. For instance, some people show normal contralateral activation of the primary motor cortex, whereas other subjects show bilateral activation of the primary motor cortices. With EEG, we can also identify these patterns, and EEG has the additional advantage that it allows for much more mobility and flexibility in different task design or experimental designs compared to fMRI. And the fact that EEG has such a high time resolution also makes it suitable at some point to apply stimulation as needed based on the EEG activity that we record. So that's why EEG in combination with t-DCS has so much potential, and we want to investigate if this can be used after stroke. Maria Carla already explained the effects of anatomical variability. And as you can see from these two images, the variability between different stroke subjects can really be large, and we should also take that into account. And we can do that with MRI images. So that's one of the things that we need if we want to individualize t-DCS after stroke. And we can use that to make head models for simulation. In addition, we need EEG recordings during some kind of task that we want t-DCS to have an effect on. And that could help us, for example, to determine if we should have ipsilesional, contralesional, or bilateral stimulation. Once we have the EEG recorded, we can do a source reconstruction to determine the brain region that is active during the task. So that's the i-tDCS target. And we can, by simulation in the realistic head models, we can determine what the optimal i-tDCS configuration is to maximally stimulate that specific target that we identified. What we haven't done so far yet is to assess the effect of this type of individualized i-tDCS on functional performance or task-related EEG correlates or any other measure that's relevant for a specific task. We can use EEG to determine the targets for i-tDCS, for instance, by looking at the difference between a passive and an active motor task, or the difference in activity between a difficult and a simple motor learning task. This allows us to really distinguish between brain areas that actively contribute to the active part of the task or the learning part of the task. And the way we can reconstruct the brain regions that we want to stimulate is by applying algorithms such as ELO-RITA, dipole fitting or beamformer that allow us to calculate back the source location and the activity that make up the channel activity that we measure at the scalp. So the way we can individualize i-tDCS then after stroke is by first recording MRI images, and these are examples of 3 different subjects. We can create head models of those. We can combine it with EEG recordings. The EEG recordings are also for each subject recorded individually. And then we can do a source reconstruction of the EEG data within the model. And we get in this case, a single point per subject that we want to optimize i-tDCS for. And then the optimization looks like this. As you can see, there are right images show the electric field on the gray matter of each subject. And in color code, you see the strength of the electric field. And these patterns all look pretty much different, but what they have in common is that they all have the maximum electric field at the target we wanted to stimulate. You may wonder why we should improve or want to use i-tDCS to improve motor learning after stroke, or why we need individualization. Because this review from 2016 indicated that i-tDCS indeed facilitates motor learning post-stroke. However, it also describes that there's a lot of variability between subjects that might be due to differences in ipsi or contralesional stimulation or bilateral stimulation, and that we don't really know when to use what type of stimulation. In order to better understand how we should target i-tDCS, we therefore created a study in healthy subjects with EEG and a motor learning task. And in this experiment, we asked healthy participants to perform a simple and a complex motor learning task. And then we performed source localization on the EEG data. And finally, we assessed the relation between learning and EEG. In these tasks, participants had to move this black cursor from left to right by pinching in a force transducer. And for both tasks, participants had to move the cursor to the targets over here. And for the complex task displayed on the left, they had to move from 1 to 5 in sequence. And for the simple task, they had to move the cursor to from the home position to the wider target 5 times in a row. So the nature of both tasks was the same, namely they had to make this pinching action, but in the left In the complex motor learning task, there would be learning, whereas in the simple task, there would only be motor activity. And with this way, we try to separate motor learning from motor activity. Here are some results of the source localized data. And what we can see here is our two clusters on the primary motor cortex, a contralateral one and the ipsilateral one. In the contralateral M1, we see almost no difference in the time frequency decomposition of the EEG data between the two tasks, which is this third panel. In the ipsilateral motor cortex, however, we see that in the beta band from about 16 to 30 Hertz, there are large differences in activation, and the suppression on the group average level is much larger during the complex learning task compared to the simple one. If we look at the individual data, then we see no differences in the contralateral motor cortex, but again, we do see in the beta band a large difference between the complex task and the simple motor learning task, indicating that the ipsilateral motor cortex is involved in motor learning in healthy subjects. And we think this information will help us to determine the role of the ipsilateral motor cortex also for stroke subjects, because it's not just that we should always try to suppress activity from the ipsilateral motor cortex, for example, but might also be assisting. So that's why we think we also need to take this into account when we design configurations for stroke subjects. In summary, MRI-based head models and EEG can be used to determine targets for i-tDCS in the chronic stroke phase. And these models can also be used to determine optimal i-tDCS configurations. In healthy subjects, ipsilateral M1 activation is also involved in motor learning. There remains a future challenge to investigate if individualized i-tDCS is indeed more effective than general i-tDCS, so without individualization after stroke. We have developed some nice additional tools that can help to perform this individualization of i-tDCS. This was my presentation. I want to thank you for your attention.
Okay, so I will now go on to show you the recording from Mana, who is taking the concept of evaluating the motor learning with EEG further towards not just the source localization, but especially the connectivity analysis. So if things go well, I can now share with you her presentation.
Hello everyone, best wishes for 2021 for all of you. I think this is the last presentation for this webinar. So I start this presentation with this topic, connectivity analysis in motor learning by using EEG signal. As a short introduction for our experiment, I can start with this slide. We designed a protocol which was contained two different tasks, simple task and complex task. During the complex task, we asked the subjects to pinch the button and move the cursor from a specific location to the specific goal and reach the specific goal with a specific number. But in a simple task, the subject just pinched the button 5 times and reach the cursor to the big rectangular as a goal. In between, we record the brain signal by using 64 EEG cap. In total, we had 20 healthy subjects in this experiment. We randomly divide them to 2 groups. Half of them start the experiment with doing the complex task, and then continue with a simple task, and half of them start the session of the experiment with a simple task, and then continue and end the session with a complex task. Also in this experiment, we recorded 2 times the resting state from the subject. The first one was exactly after preparation, before execution any task, and the second one was between the 2 different tasks. And each resting state was almost 3 minutes. The main goal of this study was looking at the functional connectivity variation down to the motor learning. This goal was divided to the 3 sub-goals. First one was find the relation between the connectivity variation and motor learning by using the data set at resting state. The second one was investigate the effect of the motor learning on the connectivity, and the last one was investigate the connectivity difference pattern in 2 different tasks, complex tasks and simple tasks. To look at the connectivity variation, we used 5 different frequency bands, which was a start from theta to high beta. Okay, I start with the resting state. As I mentioned, we had 2 resting states, and then we calculate the connectivity at these 2 resting states and use the connectivity result at these 2 resting states to answer 2 questions. Before I explain these 2 questions, I should mention that for calculating the connectivity, we consider C3 as a seed and calculate the connectivity between C3 and all other electrodes over the brain. The reason that we consider C3 as a seed was C3 is an electrode which is placed over the primary motor area, and primary motor area is an important area which is involved in the motor learning and also during the execution of task. Okay, we can back to the questions. So the first one was we use connectivity at resting state to see the effect of the motor learning by comparing the connectivity at these 2 resting states. And the second one was we try also to find the relationship between the connectivity pattern in resting state and motor learning during the execution task to see if the connectivity in the resting state or in a normal situation can predict the motor learning during the specific task. Yeah, here we had 2 different tasks, complex and simple tasks or not. Okay, in this slide, you can see the result of the comparing 2 resting states, the first and the second one. And it's supposed that the red color in top of plot show the location with a significant difference between the connectivity at the first and the second resting state. And you can see the result over the 5 frequency band. As you can see, there is no significant difference between the first and the second resting state. So the result, it means that the results show no systematic or focal difference between the connectivity at first and the second period of the resting state. So it means that based on this protocol and in our experiment, we didn't see any long-term effect of the motor learning over the connectivity because the connectivity at the second resting state was quite similar with the first connectivity, with the connectivity at the first resting state. And here you can see the result which show the relationship between the motor learning in a complex task and the functional connectivity during the resting state. We try to fit a linear regression model between these two parameters. So for instance, in this figure, you can see this relationship. And if we consider motor learning during the complex task for all the subjects as a parameters and put in a x-axis and put the connectivity value as a second parameter at the y-axis, we could fit a linear model between these two parameters, and the results show a positive relationship between these two parameters. So it means that, for instance, in this figure, if the subject in the normal situation, in our case is in a resting state, that it's supposed that the subjects don't do anything. If the subject has more connectivity between the C3 and CP5, it means that during the execution, the complex task, they can learn more this specific task. So in this topo plot, I just choose 3 frequency to show the result in this slide. And these topo plot are just plotted based on the R-square value in a linear model. R-square value is a statistical measure which show how the data is close to the fitted model. So for instance, for low beta, it means that if the subject has more connectivity between C3 and the electrode over the ipsilateral part, like C4, or parietal electrode like CP5, they can learn better the complex task. The same story for the simple task. Again, we try to just fit a linear model to this task. And also you can see that, for instance, for high beta, the subject with higher connectivity between C3 and electrode over the central or ipsilateral part over the primary motor area, they can learn better simple tasks. Now we just want to go to look at the functional connectivity difference between the two different tasks, complex and simple tasks, during the execution of the task. Here again, the red color shows a significant difference between the connectivity in simple and complex tasks. And you can see the result on just over 2 rows. The bottom row show the result in 5 frequency during the preparation of the task. We consider 500 milliseconds before execution of the task as a preparation time. As you can see in most of the frequency band, there is no significant difference between the connectivity in simple and complex tasks. This result is quite in line with our result, which was based on the resting state. In the resting state, we also show that there is no difference between the 2 resting states, because in our experiment, we didn't have any long-term effect of the motor learning. Also, we can see during the preparation, there is no difference between the complex and simple tasks. But opposite of these results, during the execution of the task, we can have a clear, significant difference between the connectivity at these 2 different tasks. For theta, for instance, for theta band, the most difference just located over the ipsilateral, central, and the frontal part, the part which are related to the planning during the motor learning. Or for alpha, high alpha or low beta, the most significant difference just located on the occipital part, which is related to the vision at the conclusion, based on our result, we didn't see any systematic difference between the connectivity in resting state in the first and the second resting state, which means that in our protocol, in our experiment, we didn't see any long-term effect of the motor learning over the connectivity. We also found a positive relationship between the connectivity in resting state and the motor learning during the execution specific task. And also we also show a significant different connectivity in complex and the simple tasks, which was mainly located on the ipsilateral and occipital part. Thank you for your attention. Unfortunately, I'm not present on the live webinar, but if you have any question, of course, my colleague will answer your questions. Thank you.
Okay, maybe I can shortly bring up, if that's okay, Leonie, this last slide to maybe quickly resume and thank the speakers. This was our research group. I hope we have been able to show you some very interesting tools to further individualize t-DCS, which I think, for example, the connectivity analysis, the basic knowledge about motor learning, about measuring motor learning with EEG, I think goes beyond only the application of t-DCS. And at the same time, I think this work also shows that if you want to apply t-DCS in stroke, you have to really carefully think about and control many between subject variations that could play a role when you apply t-DCS. So I hope that the presentations gave you an impression about this work. We're open for questions. Many of the topics were, of course, relatively introductory. So, of course, if you want to learn more, you can also contact us to and follow our publications that will be coming up soon. So for now, thank you very much, and I'll give the word back to Leonie.
Yes, well, first, thank you all for the nice presentations. I can see it's a very interesting topic. And of course, you've done a lot of work, so well done. I was wondering if there are any questions. I didn't receive any in the Q&A. Maybe somebody from the audience who has a question. So, yeah. Nobody. Okay. I will have a question because you develop nice tools. And you just said, okay, we can use them maybe in other fields as well. Do you have any examples, or where can you use your tools for other stimulation techniques? I've read about MEG as well, MEG stimulation.
Well, maybe if I can start with that, I think that that there's a lot of different applications now where you use some kind of either invasive or non-invasive brain stimulation. So there could be, there's some alternatives like i-tDCS. I think yours can maybe also present that a little bit more. I think in diseases like Parkinson, we've been working on techniques for invasive brain stimulation, and in all of these situations, you have to really consider which areas you target, why you want to target those areas, and also if you want to target a specific area, how does the conductivity of the head play a role in that? So I think if you would move to a different type of brain stimulation, either transcranial or maybe if you do it invasively, of course, the situation changes a little bit in the sense that you would be able to target specific areas much more than by transcranial situations, but still then you may not only directly change the area where you stimulate, but also a bigger area that with some modeling you could try to influence. So I think that's where some other brain stimulation techniques could benefit also from the tools that we have developed.
Okay, and for example, with the i-tDCS, you didn't get like that has a lot of influence, but do you think by developing your tools even further, like you was presented that the ipsilateral motor cortex is involved in motor learning by targeting this? Did you already try to target especially this area, or is that the next step? Or
well, it's an interesting step, I think, which we haven't taken yet, and I'm not sure if we will be able to do that within my project, but I do think it's it would be interesting to see how that would work out, and the new developments in TDCS technology also make it easier to stimulate multiple targets at the same time, which during the introduction of TDCS was not possible yet, because the most studies with TDCS used electrodes of 35 square centimeters to stimulate the brain, and with these smaller electrodes, it's easily possible to stimulate multiple targets, but that also requires the models. I think it's not straightforward how you would then optimally stimulate a combination of the contralateral and ipsilateral primary motor cortex, for instance. So these tools we use are really useful for that. But if it works, that should be tested in an experimental setting, I think.
Nice. I have another question from Parham Ebrahimi. I will unmute your microphone. So, yes.
Hello, everyone. Thank you all for your presentations. I have one question for Maria. She explained that she developed this conductivity model on a brain model to estimate the conductivity in a lesion. And if I understood correctly, you mentioned you recorded TDCS potential using EEG. And my question is now, how would you then filter out the brain activity, or how would it influence the potentials that you're recording from the TDCS?
Yeah. So far we were not able to record EEG, and so the combination of TDCS and EEG in patients. So everything that I showed was simulated, and therefore so we simulated what will be called recorded potential. So we simulated the TDCS, and so we simulated some current injected into the brain, and in combination with recording what was happening at the scalp. Okay. So far it was very tuned, and we decided what was the source, and was very controlled.
But if I may add something to this, we didn't add EEG to the simulated measurements yet, because we can, to reduce the effect of background EEG activity, we can do two things. Extend the measurement time and then average over time to reduce the effect of ongoing brain activity, or we can increase the stimulation strength such that what we measure at the scalp is due to TDCS is larger than what the brain generates itself. So those are two methods to overcome the effect of background EEG activity. It can be easily realized. So that's why we didn't take it into account just yet.
Okay, thank you.
You're welcome.
Yeah, I can imagine that the difference between the EEG activity and the electrodes, the stimulation is very big, right? Very large? Or is it like similar?
It's bigger, but yeah, it's not like you will measure millivolts at the scalp, but yeah, it's also, if you consider the EEG activity as noise, and you can sample at 2048 hertz, then it's very easy to collect a lot of data such that the random noise averages out. So it's
okay, yeah,
quite easy to overcome it.
Okay, thank you. I received another question from Amin Yangorbani. I'm sorry if I don't pronounce your last name right, so excuse me. The question is there any option to apply i-tDCS to improve the performance of sportmen?
Niels, would you want to?
I think there are studies that in which i-tDCS is applied on athletes, but I can also imagine that it maybe suffers from the same things as in stroke or in healthy subjects.
Yeah, I think it might be good to mention that if you look at the i-tDCS literature, there's a lot of different applications. And for example, I showed in my presentation at the beginning this stimulation setting where they had i-tDCS stimulation more on the frontal brain. The idea is that that's a system where you can up or down regulate, that is affected, for example, by depression, but that also has to do with attention and concentration. So for example, in sportsmen, you can, and I suppose that would be very different for different sports, you could think about if you can influence things like concentration, if you want to influence fine motor control, if you would be interested in upper or lower legs. So I think there's certainly been a lot of studies going on. I can assume, I think you would, if you would go on PubMed, find thousands of different presentations applying i-tDCS to something. It's really, I have a PubMed alert on i-tDCS, which gives me like a weekly 30, 40 i-tDCS publications. So it's a little bit difficult to really overview everything that's going on, but I think it depends a lot on what you would like to enhance in sportsmen or in patients or in any other population. And then the next question would be, I think, could you imagine a pathway where up or down regulating the brain basically could be an interesting intervention? So I think it depends a lot on your application. It also depends on which areas you may want to stimulate, because some are much more easy to target than, for example, the deeper the brain area, the more difficult it would be, or the more current it would take to really target those areas. So there's a lot of things involved there. But I'm sure you could find a lot of reviews on the applications of i-tDCS in different sports applications.
Thank you. I think that answers the question, because I also received the message. Thank you very much. Then I got another question from Hans de Weert, and it's in reference to Sumyendra Ramprasad's thesis of 2014, remodeling and simulations. I wonder if and how i-tDCS has meanwhile contributed to a better understanding of its working mechanism.
So I know the work of Sumyendra, and the question maybe is not super clear to me. So, or because it was intended to be like, what are the achievements in the modeling world that has been succeeded. Meanwhile, is it that the question? Or?
Yeah. I think how the remodeling and simulations, how they are already contributed to the better working mechanism of i-tDCS.
Well, I think maybe if I can try to answer some of that, I think one of the things that these simulation works have learned us is that it's not so straightforward to think about where you would want to stimulate and then just place electrodes. So I think even before the work of Sumyendra, and there's been other work also internationally, people tended to think that if you would want to excite the motor area, you would place an anode over the motor area that you would want to stimulate and just place the reference somewhere else. While from this work, we have learned, for example, that the region that the brain region that is optimally stimulated is really much more somewhere in between, and it can be quite complicated depending on the brain anatomy where you would need to place your electrodes. So I think that the modeling work has already and is continuing to help us learn where you need to stimulate and also what you can expect from a specific combination of electrode location and stimulation intensity. And then there's questions about is it most important to either maximally stimulate an area, or is the direction very important? I think that in general, the simulation work has learned us a lot more about what do we actually target when we do something.
And also about the working mechanism. I think most early t-DCS studies usually have a functional measure. So that could be, if I also see the next question, something about reaction time or movement speed, things like that. But they don't really help in explaining the mechanism of t-DCS. And now in more recent studies, it's possible to combine t-DCS with EEG, and I think that will be an important step to also understand the working mechanism of t-DCS, because it may be a less noisy environment and it's more closer to the source of the brain activity, because we can measure the brain activity itself. So I think from that perspective, we can maybe make a nice step forward to understand what t-DCS is doing, both on functional tasks, but also on experiments in which TMS is used to assess the effects of t-DCS. With large electrodes, it's difficult to combine those kind of experiments with EEG. Well, that's one of the techniques that could tell us more about the working mechanism of t-DCS.
Well, thank you for your answer. I hope that answers the question. We received another one from Mohammed El-Kholi. Is the reaction time for each person can be considered as an important parameter that might affect on the results?
Do you mean in the reaction time as a performance measure to test the effects of t-DCS, or more as a factor that can explain if t-DCS works?
I am not sure. Maybe Mohammed can explain, elaborate a bit more.
Mohammed's still muted. I don't know if we can.
Yeah, I asked to unmute, but.
Yeah.
Mohammed, can you
say that I don't exactly understand this question, so I find it difficult to answer indeed. I have a problem in voice, Mohammed says. Maybe if it would apply to your motor learning task, yours?
Well, we developed a motor learning task because we knew that it would not allow for a ceiling effect in performance. And that's why we think it was suitable for learning. And that's why we also think it would be a suitable task to assess the effects of t-DCS, because people can keep on learning. While for reaction time, I don't think it takes a whole lot of repetitions of a certain movement to have a ceiling effect on reaction time. That makes it also difficult to find the t-DCS effect, because if people will maximally perform very fast into your experiment, then it's difficult to see if t-DCS has a positive effect on that. So I think it's when you want to assess the effects of t-DCS, it's important that you do that in a measure that does not suffer from ceiling effects early into the experiment. So that's, don't know if that answers your question. I can at least imagine that having reaction time as an outcome measure might be difficult to find the t-DCS effect, and then you will easily find no effect because it will improve, reach a ceiling effect regardless of whether you applied a sham condition or an enhancing condition.
Okay, thank you, thank you. Yes, to answer the question, I can see. I don't know if there are any more questions. I didn't receive anything else. I don't know. Otherwise, maybe we could bring this webinar to an end. Yeah, then I really would like to thank our speakers of today for their effort and time and the clear presentations. Yes, so thank you. It was really interesting having 4 speakers, so it was really good. Thank you so much. And then for our next webinar, it is not arranged yet, but as soon as we have something, we will publish it on our website and through LinkedIn, and also in our newsletter, so stay tuned. For more information, you can find the related literature on our website as well. And then I would like to thank you all for being present, and I hope you have a nice day, and hopefully see you next time. And thank you again for our presenters.
Okay. Thank you very much. And thank also the audience for being here. Please contact us if you have any more questions.
Yes.
Thank you.
Okay. Bye-bye.
Bye-bye.
Bye.